Hey everyone. For this video, let's jump right into an experiment with light. Suppose we fire a laser at a barrier that has two slits that are very, very close together. We're going to fire the light through these two slits and we want to know what's going to show up on a screen that we set behind these slits. So our diagram is going to look like this. We've got a laser, so we're going to be using an actual laser over here. We fire that at an aperture that has those two slits in it. So the laser is going to hit that aperture and some of that light is going to go through. And we wanted to try to identify what is going to show up on the screen behind it. So you might want to spend a minute to think about what you think the outcome of this experiment is going to be, but let's kind of go through how we're actually going to do this experiment. So as I said, I've got a laser over here. This is a helium neon laser. I'm going to be firing that laser at a barrier that I've set up. It's going to be exactly 2 meters away from this aperture that we're using. And the aperture that we're using is going to be this plate. Now, this is probably going to be too hard to see on this video, so on the screen to the side, I'm going to take a picture of this plate and show that under D and E, there should be each one of those should have two very, very closely spaced slits. Again, under both D and E. For D, they are really, really close together. For E, they're a little bit further apart, but each one of those only has 2 slits under each of those letters. So this is what we're going to fire the laser into. So that's going to be our aperture, and we're going to see what shows up on the screen. So I'm going to change the lighting in here so we can actually see the laser beam a little bit more, get a second camera set up so we can see a better view than just this camera. So let's set up this experiment. Okay, so let's take a look at this experimental setup in a bit more detail. So I've got my second camera set up, so hopefully we can see this from 2 different angles. The laser is going to be aimed at the screen on the far side, so hopefully when I turn on the laser, hopefully this should be nicely centered. The center of that laser is right on the 50 centimeter mark, and notice that that screen is going to be exactly 2 meters away, from where I put this barrier. So we're going to use this barrier and see what happens when I shine the light through the 2 slits that are right under D. So let me write a couple of things on here. We're using D first. So we're using D. And the distance between those slits is 2 meters. So here we go. I'm going to put this right here and make sure I line this up as nicely as possible and aim so it's going right under D. So hopefully that's clear that that's aimed at D. And let me move this camera. Hopefully I don't run into anything. So you can see what's on the other screen. So all I've done is aim that laser through that spot D, through those 2 slits. And what do we end up getting over here? Well, we notice that we get this repeating pattern of bright and dark bands. So we get a bright spot right in the middle. And then as we go to either side, we get this repeating pattern of bright and dark bands. Now, notice that that pattern continues quite a while. It becomes fainter and fainter, but if I kind of block out some of the light from behind, I can even see a couple of dots. So they're really, really faint, but I do see a couple of dots over here. So the result that we seem to get from this demonstration is that we get this repeating pattern of bright dots. Not just 2 dots like we might expect from our intuition. And we want to know, well, why does this happen? You know, our intuition would probably say if there are 2 slits there, well, the light could go through one slit or the other slit, so we should get 2 dots on the far screen. But that doesn't happen. Our intuition doesn't work in this case because our intuition is based on our prior experience, our everyday experience, and most of us probably don't have a lot of prior experience with firing lasers through 2 slits. So why does this happen? What was the cause of this particular pattern? Well, in the last scientific critical thinking videos, I talked a little bit about falsifiability and different kinds of models. And if I were to say something like, oh, this was magic, well, not only can we not really test that, it doesn't give us anywhere to go. If I said that this pattern was produced by magic, well, okay, what would happen if I change some set, if I change the laser light, if I change something about the spacing of those slits? If I go with something, again, not really physical, I have no way of building a model from that has predictive power. So magic, even if it is magic that's doing this, that's not going to be a useful explanation. We can't solve a mystery by appealing to a bigger mystery. So what might be a better way of approaching this? Let's say we consider a wave model of light. Instead of light acting like a stream of particles, we're going to think of light as acting like a wave and see if that gives us some predictive power. So I'm going to try to model this with some material that I have here. So hopefully I can get this set up decently. There we go. And I'll also use this second camera to kind of show what I'm working on here. So let's say I'm treating light like a wave, and that wave has a bunch of wave crests. So this transparency, we're considering the wave properties of this to be, the blue is where the wave crests would be, and the clear parts are where the valleys are going to be. Okay. So this is giving off waves in all directions. Well, what if I took a second wave and had it interacting with this first wave? Okay. So now I've just got two waves that are interacting with each other. And we notice a couple of really interesting properties. One is that when I have these two waves interacting, there are going to be certain regions where those waves seem to be lining up with each other, and that is when we would get a very strong interaction. This is called constructive interference. If I have two waves and we get crests meeting crests and valleys meeting valleys, for waves, that's kind of going to make super crests and super valleys. So along this direction, we get constructive interference, and that would show up as a bright dot. In other directions, we'd also get constructive interference. Wherever the crests of both of the waves match up and the valleys of both of the waves match up, we're going to get that kind of constructive interference, and those are going to be our bright dots. However, in other directions, along, say, this line, that is going to, right now we're getting the crests of one wave matching up with the valleys of the other wave. Okay? So along here, and here, and here, and here, things like that, those are going to be dark sections. That's going to be destructive interference, and the light is going to kind of cancel out. So if light has these wave-like properties, and the slit acts like two wave sources, we get this thing that we call an interference pattern. It's sending out these two waves, and based on how those waves are interacting with each other, we are going to get these repeating patterns of bright spots when the waves are helping each other out, and dark spots where the waves are canceling each other out. Now, we also want to ask, so if we have these two close together wave sources, when those two waves interfere, we get this repeating pattern of bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. Instead of just getting two waves showing up, we get this repeating pattern of bright and dark bands, which seems to match up fairly well with what we got when we actually looked at this laser. So it seems like this might be a plausible model, but in order for us to have confidence in this model, we must be able to make testable predictions. In this particular model, if this wave interference is actually going the way that this model predicts, well, different points on the screen are going to be at different distances from each of the two slits. So when that laser light is going through each of those two slits, one of the slits is going to be a little bit further away from a particular part on the screen than the other slit. Well, if that is some integer number of wavelengths of the light, then we're going to have gone through one full wavelength, and if this is giving off a crest, this crest is going to match up with it, and those waves are going to be nicely aligned, and we're going to get constructive interference. So based on this model, we're not going to go into the full math for this, but based on this model, if I have any integer m, we're going to get bright bands whenever the distance between the slits times the sine of the angle that this light is being diffracted at is equal to some integer m times the wavelength of that light. But what other predictions does this make? So we're going to test out that one, but let's do a quicker prediction first. So right now, when these two wave sources are really close together, we get this repeating pattern of bright and dark bands. What happens to that pattern if I move the two sources further away from each other? Well, if I move the two sources further away from each other, notice that that pattern of bright and dark bands gets a lot closer together. So if these two sources are really close together, that pattern of bright and dark bands should be more spread out. If those two sources are further away from each other, that pattern of bright and dark bands should be closer together. This gives us a way of actually making a prediction for what should happen if I change this particular setup, if I change how far the slits are apart from each other. So let's give that one a try. So let's set up this exact same experiment again. I still have the laser set up so that when I turn on that laser, the laser light is aimed right at the 50 centimeter mark. Let me move my camera just a little bit so we can see this just a little bit better. There we go. So the laser is still centered on the 50 centimeter mark, and this screen is still exactly 2 meters away. This barrier is still exactly 2 meters away from the screen. And let's measure some of the properties of this light that we see over here. Okay. So right now we're using slit D, and on the manufacturer's label, for D, the distance between those two slits is equal to 0.125 millimeters. Okay, that's for when we're using slit D on that barrier that we had. And now over here, we want to measure where are we getting some of these bright bands. Now, just for simplicity, I'm going to try to measure how far from the central fringe is the 10th bright band. So we're starting from here, we're going, would be the 0th band, m equals 0, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, that one's kind of hard to see, 9, and 10. And that looks like it's just past 60 centimeters, so going from here to here, that would be about probably about 10.1 centimeters to get to that band. So let's write that down. For the 10th band, so that would be m equals 10 for this, that 10th band was exactly 10.1 centimeters from the bright central fringe. Let's do the same kind of thing. We're going to do the same thing, but instead of using slit D, I'm going to change this to slit E. Now for slit E, we're going to do the same kind of thing, but for slit E, the manufacturer's label said the distance between those slits was actually a little bit larger, so 0.250 millimeters. And based on our previous observations, based on this model that we are trying to develop, this wave model of light, if those dots get further apart, those bright bands should get closer together. So when we look at the 10th band, it should be smaller than 10.1 centimeters. Well, let's replace it. So I'm going to move this over, and instead of looking at D, we're going to look under slit E. I'll get that aimed properly. There we go. Okay, so I've got that aimed. Again, we are looking under slit E this time. If we go over here, well, notice that these dots are now much more closely packed together. So if I'm starting from that bright central fringe, this one here, we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right around 5 centimeters, but I'm going to go even further just to make sure that we get better measurements. If I'm measuring larger things, it's going to be easier to measure. So that was 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, now 20 is right past the 60 centimeter mark. So now it looks like n equals 20 gives us that maybe 60.1 or maybe 60.2 for that. It's a little bit difficult to measure exactly. Let's call that 60 point. So that would be from 50 to 60.2 centimeters. That would be 10.2 centimeters. So let's write that one down. So for E, for the m equals 20 line, that I'm going to call this distance x for both of these. That x distance was 10.2 centimeters. So notice that when I increased the distance between those two slits, that diffraction pattern got closer together. That matches with our prediction based on this model of this wave model of light. When I have a slit separation that is larger, that diffraction pattern should get more closely packed together. But let's actually go through the numbers for this and see. So before we do that, I'm just going to do a quick side-by-side comparison. I'm going to move the camera over here, and I'll move this camera over here. Aim it this way. So this was the case for E when the two slits were further apart, and this is the case for D when the two slits are closer together. So when the slits are closer together, that diffraction pattern is a little bit more spread out. When the slits are further apart, well, that diffraction pattern is going to be closer together. And that matches what the wave model of light would have predicted, but let's see if we can go into this in a little bit more specific measured detail. So again, let's see if we can specifically put this particular model to a more specific test by putting particular numbers in here. So in our first test, when we used the aperture for D, the manufacturer's label says, again, that for D, there should be two slits, and the separation between the slits from center to center should be 0.125 millimeters. So 0.125 millimeters, so let's write that one down. So on this equation, little d would be 0.125 millimeters. And we need to be able to measure the diffraction angle. What was the angle at which that 10th band showed up? Because we were using m equals 10, and we need to figure out this angle this angle theta. So we can use some trigonometry because this is a right angle triangle, and we can say, well, the tangent of that angle should be the opposite side, the 0.101 meters, divided by the adjacent side, the 2 meters. Okay. So if I rearrange this, do that division, so 0.101 divided by 2, and then take the inverse tangent of both sides. When I take the inverse tangent, I get my angle as being 2.89 degrees for that diffraction angle. Okay. And let's see if we can take this information together and figure out what is the wavelength what is the wavelength of this particular laser, this helium neon laser? Okay. So we're saying that we should have d times the sine of that angle theta equals m times the wavelength. Well, that distance was 0.125 millimeters times the sine of 2.89 degrees equals 10, because that's which band we were looking at, times the wavelength of this light. Well, if I do 0.125 times the sine of 2.89, I get 0.00630 equals 10 times lambda. And if I divide both sides by 10, I get the wavelength of 0.000630 millimeters. Because right now this would still be in millimeters because we were using millimeters up here. Well, if I multiply that by 1,000, that would give me the wavelength in micrometers. And if I multiplied it by 1,000 again, that would give me the wavelength in nanometers. So if I take this and multiply by 1,000,000, that will give me 630 nanometers for the wavelength of this light. Okay. Again, this is a helium neon laser, and this kind of laser has a particular wavelength. So if we look up helium neon lasers, the best known and most widely used helium neon lasers operate at a wavelength of 632.8 nanometers. So the true wavelength, well, let me scroll back down. The true wavelength should be 632.8 nanometers. We got 630. I'd say that's a pretty close match on the manufacturer's measurement of what is the wavelength of a helium neon laser and what we got by measuring this particular diffraction effect using this wave model of light. We get very, very accurate agreement between those two measurements. In fact, let's try the case for E. So for E, let's change this around. Well, again, on the manufacturer's label, the spacing between those slits should be 0.25 millimeters. Let me bring that up again just so we can verify that. So for pattern E, 2 slits, separation distance of 0.25 millimeters. Okay. So that one is 0.25 millimeters. This case, we were looking at n equals 20. And for measuring that angle, well, the screen was still 2 meters away. The distance along the screen, we said that was 10.2 centimeters, so 0.102 meters. And if we run that, so 0.102 divided by 2 and take the inverse tangent, looks like that angle is 2.92 degrees. And we are once again subbing that information into this equation to see if we can get another way, another sample for measuring what is the wavelength of this light. Well, that's going to be 0.25 millimeters times the sine of 2.92 equals 20 times that wavelength. So 0.25 times the sine of 2.92, I got 0.0127 millimeters equals 20 times the wavelength. And if I divide both sides by 20, in this case, my wavelength ends up being 0.000637. And that would be millimeters, which is the same as 637 nanometers. Notice again, we're still getting very good agreement. I think this is less than 1% off. We're still getting very good agreement between the true wavelength of the light and the wavelength that we measured using this diffraction effect. Again, it would be very, very unlikely for these numbers to have worked out so nicely and matched up with each other if this was purely by chance. So this is data that supports this wave model of light, and this wave model of light makes testable predictions. If I were to change the slit separation distance, we could predict where different bands are going to show up. Or if I'm using different lasers, I can use the slit separation distance and the diffraction angles to measure the wavelength. If I know the wavelength and the diffraction angle, I could measure the slit separation distance. There's a lot of different ways that we could rearrange this equation to make predictions for new experiments and new kinds of observations. So to finish this off, let's talk about some practical applications of this particular model, this wave model of light. We can use this diffraction effect to break up light by wavelength. This equation, if I have different wavelengths of light and the same diffraction grading, they'll be dispersed by different amounts. So, for example, let's say I take my camera and I aim it through this diffraction grating. We can notice that it's able to take the white light coming through the windows and break it into its constituent wavelengths. This is the basis for spectroscopy. Basically a hugely applicable area of chemistry where we can identify chemicals by the different spectras that they're producing, identify the properties of those materials. It's an extremely useful application for talking about how light and matter will interact with each other. We can also use this to measure very, very small scale objects, down to molecular sizes in the case of X-ray crystallography. So let's look at this particularly with a CD and a DVD. And I'm going to take the laser and aim that laser. Let's start with the CD. So I'm going to aim the laser at the surface of the CD. And you can see that when I aim the laser at the surface of the CD, that light that's reflected off of there, it's being diffracted. We're getting all sorts of these patterns showing up. And what's happening is the grooves in that CD, all the little grooves where the data is encoded, all of those are acting like those two slits and causing that light to diffract in different ways. Okay. The DVD does the same sort of thing, but let's look at its effect. If I look at the DVD, notice those dots are a lot further apart from each other. Well, let's back up a second. When I look at the CD, we get lots of dots pretty close together. When I look at the DVD, the dots are much further apart. I'm trying to see if I can get a dot showing up on the other side, but not showing up super well. There we go. Well, if I back up, we said that if that diffraction pattern is closer together, then the slit separation distance is larger. For the CD, that diffraction pattern is closer together. Those bright spots that are showing up, they're showing up closer together, which means the spacing of the slits on this CD is a lot further apart. There's less data that can fit onto a CD than you can fit onto a DVD. Because again, for the DVD, when I shine the light on here, that diffraction pattern is much, much more spread out. Can I get the one? Oh, got the other one just for a second. So there's one on the other side starting to show up. I have to kind of aim this properly in order to get that diffraction effect. But the basic idea here is I can measure very, very small scale distances using this diffraction effect. And if I use very, very short wavelength light, for example, X-ray light, I can measure distances down to the atomic scale. So if I want to measure the properties of a crystal, the different layers of atoms in that crystal will act like these slit separation distances. So this is where X-ray crystallography comes in. This also affects the maximum performance of optical devices like telescopes. So, for example, in pictures from the Hubble telescope or the James Webb telescope, when you sometimes see those spikes on objects, kind of a cross spike for Hubble images and kind of that 6 spike with the 2 extra little smaller spikes on the side. That has to do with how light is diffracting around certain structures inside of the telescope itself. We have to be able to take that into account if we're going to understand how these telescopes are making their observations. So again, there's a lot of applications for this, for looking at light as a wave phenomenon. It does get more complicated when we talk about quantum mechanics, where light comes in individual packets of energy. So we have individual photons of light, and this is going to get into the particle wave duality of light, that it sometimes has properties like a particle and sometimes has properties like a wave. But that comes a little bit later when we have more data, because again, we are always going to learn more things when we have more good data, and we can always try to improve our models. So we'll call that good for today. Again, hope everyone's doing well, and if you have questions about this these topics that we're going through, feel free to throw those into the comments below. I try to answer those as often as possible, or maybe another helpful person who's watching these might be able to answer some of your questions as well. And thank you as always for your attention, and have a good rest of your day.